It's now time for us to start dealing with more realistic functions, that is, functions closer to real-world applications. Our world is three-dimensional, and in fact, if you're doing relativity theory, then your world is four-dimensional space-time. So we need to work with real-valued functions of several variables. First, I want to examine some very specific functions which come from the real world. Consider the volume of a right circular cylinder. It has a radius r and a height h. If we calculate its volume, we use the formula V of r and h is pi r squared h. If we calculate its surface area, that requires adding the surface area of the two end disks to the surface area of the cylindrical surface. Unfolded, it looks like this. From the picture, we see that the surface area is given by the function of two variables, s of r and h, equal to 2 pi r squared, adding up the surface areas of the two disks, plus 2 pi r h, the surface area contributed by the cylindrical sides. So functions of two variables occur quite naturally in geometry. As an example of a function of three variables, think of the volume of a rectangular block with sides x, y, z. Then the volume is given by the function of three variables. V of x, y, and z is just the product, x times y times z. The surface area of that block is given by s of x, y, and z equal 2xy plus 2yz plus 2xz. Now, for a more interesting example, think of a cube being heated on one side by an external heat source, with the other three sides held at 0 degrees Celsius. This is the type of heating experienced by a spacecraft with the sun providing the external heat source. Let's place our cube with a corner at the origin of a three-dimensional coordinate system and the heated side lying in the xy plane. Then the temperature inside the cube varies from point to point, so it is a function of location and time, and four variables are needed. The temperature, capital T, will be given by some function of location and time, that is, a function capital T of x, y, z, and t for time. It is an amazing fact that we can determine the temperature at any point and any time if we know the amount of heat being provided by the external source, using ideas developed by Joseph Fourier in the 1800s. Functions of even more variables occur in fields as diverse as economics and nutrition. For example, suppose you need to feed an army. So you list the minimum daily requirements for vitamins, protein, carbohydrates, fats, and so on, and multiply by the number of people you need to feed. Now you list your foods. There are hundreds you can use, each with a contribution to make, and each with a cost per gram or liter. Which foods should you use to provide the minimum daily requirements at least cost? The number of variables here is in the hundreds, all possible foods you can use. Around 1947, the solution of this problem led the American mathematician George Dantzig to invent a technique called linear programming. In fact, the Russian mathematician Leonid Kantorovich had developed the same method in 1939 for optimizing production in the Russian plywood industry. In 1975, Kantorovich received the Nobel Prize in Economics for his work. At this stage, we just want to learn to identify the domain and range of a function of several variables, and we want to begin to graph functions of two variables. For domain and range, we just need to keep in mind the same fundamentals we used when working with functions of one variable. For example, we know that f of x equal tan x has domain the real line with all odd multiples of pi over 2 removed. So, if we are considering the function h of xy equal to the tangent of x plus y, then the domain is all of the xy plane with the point satisfying x plus y equals an odd multiple of pi over 2 removed. These are, of course, straight lines. At first, describing this domain seems intimidating, but you need to deal with it in a piecemeal manner. Start with a single singularity, say x plus y equals pi over 2, and you can graph that, and then deal with the second, and after a few concrete cases, you see the pattern. Now we can graph any real-valued function of two variables, f of x, y, in the three-dimensional xyz space by setting z equal h of x, y above each point with coordinates x, y. For our specific function tan of x plus y, the graph looks like this. Notice that we have a surface as the graph, whereas a function of one variable gives a curve. Now consider just a slight variation. G of xy equals the tangent of the product xy, which will have domain consisting of all points in the xy plane, with all points satisfying x times y equals an odd multiple of pi over 2 removed. Now instead of straight lines, we get hyperbolas removed from the plane, and the graph of g of xy looks like this. The same kind of analysis can be applied to functions of several variables which involve the logarithm. For example, consider the function p of xy equal to the natural log of x squared plus y squared minus 4. Since the function log u has domain u positive, our function p will have domain x squared plus y squared minus 4 positive, which is the same as saying that x squared plus y squared has to exceed 4. And this just says that the point with coordinates x, y has to be a distance greater than 2 from the origin, so we can sketch the domain. And in fact, we can sketch the function. The function p of xy is just the log of r squared minus 4, where r is our distance from the origin, so we can just use our knowledge of the graph of the logarithm function to graph this function. At this point in our course, we just want you to be able to identify domain and range, and perhaps give a rough idea of what the graph looks like if it is a function of two variables. So lots of practice is called for. One last example is a function which is very useful in mathematical logic, in theoretical computer science, and in probability theory. Given any set A in any universe U, the indicator function for the set A is just the function which has the value 1 at any member of A and the value of 0 on the complement of A. The indicator function is usually written with the symbol 1 subscript A. For example, on the real line, the indicator function for the half-open interval minus 1, 2, including the point minus 1, is 0 if x is less than minus 1, 1 on that interval, and 0 if x is greater than or equal to 2. Here's the graph. In the xy plane, if A is the set of points with coordinates x, y, satisfying x minus 2 quantity squared plus y minus 1 quantity squared less than or equal to 4, then the set A looks like this. It's a circle of radius 2 centered on the point 2, 1. And the graph of the indicator function looks like this. Another example. Let A be the set of points in the plane with coordinates x, y, for which the absolute value of x is less than 1. Well, there's no restriction at all on y, and we're asking that x lie between minus 1 and 1, so the set A looks like this. Then the indicator function is 0 on any point with x-coordinate less than or equal to minus 1. It's 1 if the x-coordinate lies strictly between minus 1 and 1, and it's 0 if the x-coordinate exceeds 1. And we can sketch its graph. As a last example of an indicator function, let B be the finite set of points in the plane with coordinates 2, 3, the origin 0, 0, and coordinates minus 1, minus 2, 3 points. Then the graph of the indicator function for B is just a set of 3 vertical lines of length 1 to indicate where the function has that value. Now, up to this point, all of our functions of several variables have been real valued. But in fact, we can describe functions from any dimension into any other dimension. As a real-world motivation, think of an electric field in three-dimensional space. The value of this field at a point, let's call it E of x, y, and z, represents the force on a particle of unit positive electrical charge if it were placed at that point. So the value of this function is a vector. The direction of the vector tells us in which direction the particle would be pushed, and the length of the vector tells us the strength of the push. Here is a picture of the electrical field generated by a positive charge placed at the origin. The force is in the radial direction away from the origin, and its strength decreases as 1 over r squared, where r is distance from the origin. So in general, this function would be described by its 3 component functions. E of x, y, and z will be a vector, f, g, and h, each depending on x, y, and z. Each of these functions, f, g, and h, is just a real-valued function. So the study of these vector-valued functions reduces in large part to the study of the real-valued component functions. For example, if you need to find the domain of the function e of x, y, z with x component xy minus z squared, y component log of the product x and y, and z component 1 over z minus 1, then you just need to find the domain of each component function and take the intersection of these 3 domains, because all 3 components must be defined on the domain of E. The first component function, f of x, y, z, equal xy minus z squared, has domain the entire real line. The second component function, g of x, y, z, which is the log of xy, has domain all points x, y, z for which the product xy is positive, so both x and y must be non-zero. The third component function, h of x, y, and z, is equal to 1 over z minus 1, has domain all x, y, z with z different from 1. So the domain of the vector function e of x, y, z is the intersection of these 3 domains in R3. That's the set of all points x, y, z for which the product xy is positive and z is different from 1.